All right, thanks. It has its advantages, like multiple screens, and disadvantages, like that huge column right in the middle. It shouldn't bother us because you don't really need to look at me. You can pick any screen and just look at the screen. And of course, we start from a question. What do you think? You can take this seat, yeah, anywhere. It doesn't really matter. We've learned two equations, and well, we've learned much more stuff than just two of these equations. But these are very similar, right? And as we know in physics, every word matters. We need to know the exact meaning of exact variable of each equation. In this equation and in that equation, we have the same letter. Does it, in a way? No? Okay, because you can move if you want to. That screen actually probably closer. I don't know. It doesn't matter. And let's see. Let's see what's happening here. Let's see. So this camera is supposed to capture the screen, but just in case I also have a backup camera. Actually, two. Just in case. Always have a backup. And a backup for the backup. All right. 17 versus 8. Well, let's wait a little bit longer. And in physics, every single phenomenon, every single situation comes from experiments, from observations. That's things we can see. And for everything we can see, we can draw a picture always. So it's very helpful to draw a picture which would represent what is happening when we have to use that equation, and which would represent what is happening when we use this equation. And if you have exactly the same picture both times, that means everything should be the same. But if you have slightly different picture, that means there might be some difference. For example, for the equation on the left, what picture would you draw? What should it show? Two charges, yeah. There's, well, point charge number 1, point charge number 2. And what does R mean? The distance between the two charges. That's exactly what we need to be able to say out loud. In that equation, actually Coulomb's law, this variable represents the distance between the two charges. What picture should you draw for the second equation? How many charges? Yes. Only one charge. Well, but if I just keep this dot and nothing else, how do I show a distance? Yes.
You put a dot with a line.
What does this dot represent? No. A dot cannot represent the distance. A distance is usually something long. What does this dot represent?
Point in space.
A point in space, or location, exactly. And R in this equation represents what?
The point in space of a large vector.
The distance from the charge to that location. At that location, we are measuring or calculating this thing. This thing has a name, right? How do we call it? You don't have to look, because it's, you know, sitting like this for 90 minutes might be hard. Just look at that screen. How do we call it? What's the name for this physical quantity? Electric field, well, technically electric field strength. That is correct. So this is the distance between two charges. This is a distance from a charge to a point. So how do we answer this question? And if you know the difference, and if you know the exact meaning, you're all set. And I've seen people who couldn't say the exact meaning and made mistakes. Well, moving on. Now, two more questions at the same time. Again, about the meaning. What do you think? And you know the rule. If you know what to do, you just do it. If you're not sure, you should ask a question. So if you're not sure about something, about a meaning, about a term, you should ask a question, right? If you're not asking a question, that means you know everything and you're absolutely sure what you're doing. Nothing else might exist. That's either or, right? So it's nice to be so close to everyone. No one can escape me today. So, any questions about a question or questions on the screen? So you know what potential difference is, that word voltage. You know what it means.
Well, I have a question about the question.
Okay.
You're asking.
So did you already enter your answer? Thinking, that's the wrong thing to do in physics. You know, thinking is not required. It's about almost never. You know, you answer. You don't know, you search or ask until you know it, and then that's it. So I've mentioned that word voltage a couple of times, but I didn't give you an official definition of that. If you don't have an official definition, that means you cannot answer the question on the left. So you should ask or tell, what is voltage? No, the unit is volts. Yeah, this is a different word, voltage. And if you're not sure, the fastest way to do is what? Yeah. So did you? Why? Well, what is voltage? If you don't know, you can't answer this question. If you really want to answer this question, you should find it out. And in this room, it's very easy to do. Well, you have phones and tablets and computers, right? So please, anyone, tell me a definition of voltage. Did you do your search? What is it? Okay, so what is it? It is equal to potential difference. You are absolutely right. But the official definition is slightly different, right? If you Google, if you do a search, if you read the textbook, the voltage is equal to amount of work done to move a positive 1 coulomb charge from one space to another space. So that's how it's been defined 100 years ago. But right now, of course, if we apply this rule, that will tell us that voltage and potential difference should be the same thing. However, if voltage is potential difference and potential just can't be the same thing. Yeah, it even sounds differently. Potential difference. And it's very important to remember this, this difference about potential difference. Because if you confuse those variables, you might make a mistake, that's it. It's very important to stick literally to a definition of every single physical variable, and you will be all set. It's much more important than thinking. All right, so if your computer has it, good. If not, you can join somewhere else. And this is the applet we're going to use a couple of more times today. How does it work? Well, you can, oops, first erase. You can check and check anything you want to, and you can, let's check all of them. You can see a lot of stuff happening in real time. You can attach probes to the plates. And right now, of course, the capacitor has no charge. But if I charge it up, if I connect it to a battery, what's happening? Well, it's very important to understand that a battery doesn't create any charge. It acts like a pump. So right now here, this battery generates electric field, which is actually inside the wires and also between the plates. That electric field starts acting on electrons. As we know, protons never move. So electrons will be traveling how? Well, from one plate onto another. That's it. That's how we break the neutral state. And if we have one electron moved away and brought here, and then another, and another, and another, the number of electrons one plate loses will be equal to the number of electrons second plate gains, absorbs. So the magnitude of the charge will be the same. Well, we're assuming same size, same shape, everything the same. But the polarity will be different. And to move a charge in space, we have to do some work. And that's what we call charging a capacitor. In this situation, the source of energy is chemical reactions inside the battery. That's it. We'll talk about batteries very soon again. We know that the amount of work doesn't depend on the trajectory. We can bring it like this. We can bring it like this. The work is only related to the potential difference for the charge to travel through. And we can see what is happening to charge, energy, capacitance. You can move plates closer and farther away and read everything we want to. I will ask a question later. Here, the point is to charge a capacitor, some work has to be done. And here, we should use our imagination. So we start from a neutral state, and then what do? Take electron and move it. Well, actually, from here to here. I want to make this plate positively charged and this plate negatively charged. So I take one electron and bring it over here, second, third, fourth, etc., etc. But every time when I move an electron, I do work. The problem is it's different. Because when we have no electrons, no electric field, a certain amount of work, well, actually, no electric field, zero work at first. But then we have one electron here, one missing electron here, electric field. So we have to do some work. But now we have different number of electrons, so we have to do every time slightly different work. To calculate total work, actually, we just need to use the same equation we've used for a single charge. We just need to use the average potential difference. We start from zero, and we end up finally with certain voltage. So if we want to calculate the work, all we need is average voltage, total charge. In this simple situation, for the average voltage, Oops. We can use the actual mathematical average. And that gives us the equation for the energy we store in the capacitor. This equation can be rewritten. We know that, well, from last week class, that these variables are also related. The amount of charge is proportional to the potential difference, and the coefficient we call the capacitance. So we can replace a charge with this product, and that gives us second way for calculating energy stored in the capacitor. Or we can solve the same expression for the voltage, and that gives us the third expression for the energy stored in the capacitor. That's algebra. Good exercise at home. It would take 5 minutes. But now we have three equations which we can use to calculate the energy stored in the capacitor. Which do we use depends on convenience. Yeah, of course, if I already know Q and delta V, I would use this. If I know C and delta V, I would use this. It just saves an extra step, saves time. I wouldn't use, if I could have used a definition of capacitance as well, but it's a time-saving approach. Now, let's finish this problem. We have solved it on Friday. In this situation, what do we know? The area of each plate, the distance between the plates, remember? It's been filled up with wax, and for wax we know the dielectric constant. So the calculation gave us the capacitance of the capacitor and the charge. Well, now, of course, we can make an extra step. We can calculate how much energy we have stored in it. Energy. And it is completely up to you. So you can look it up. Write down in your notebook any number you want to use for calculating energy in a minute. I'm going to switch to the next slide, and you're going to use your numbers to calculate that energy. That's it. Would be nice if we also could project the screen to your computer directly. That's impossible so far. All right, I'm going to move on to the next slide, right? So you've got all the data. Now you should calculate the energy and tell me the number. That's it. Please, help me. I really need to know that energy. I really need energy. That's why I drink coffee. the unit for capacitance farads, and a little p means pica, that bless you, 10 to the negative 12th. And people use different letter for that unit, a Greek letter phi or just a regular F. In this example, we can use all three equations immediately because we know all variables. And it's a good check. You can try calculating it 3 times if you want to. If you get exactly the same number every time, that means you do everything right, everything good. Did you get the energy? Why?
I was thinking.
I was thinking. The worst thing you could tell me. There is no, at this point, really nothing to think about. Yeah? You have to act. Take a pen, a pencil, choose equation of your, choice. Select one. Which do you want? First, second, or third? Tell me. Third. Perfect. Now write it down. I'm watching you. Okay. This action doesn't require thinking. Now, what you can do? Okay, plug in numbers in. Charge. And I need to square it. And how should I show what do I want to square? If I just write a 2. Exactly. 2 times capacitance. Now I want to point at fact, very important fact, but we've seen this situation many, many times before. A same letter, C. C. 2 completely different meanings. Here it means what? Coulombs. This letter represents the capacitance of a capacitor. So when we write the letter, we need to know what it means. Otherwise, we again can make a mistake. Farads. If I use units, I don't really need. I know in the end, if I use international system of units, I'm going to get joules. So now you have to take a calculator. Oh yeah, you're ahead of me. And please calculate the energy and tell me. So joules. I know it's supposed to be a number, 10 to a certain power. All right. Do you have the same number? Any questions? What was you thinking about? All right. I'm just gonna point. I didn't do it. I just pointed at how it could be done. This equation should be used to replace either a charge or a voltage. That's algebra. It's a good exercise to do at home. Okay. All right. All right. This is the question I want to ask. And for this question, you should use the applet. You can join forces, work together. we know that if we make a change like distance between the plates or the area of the plates, that change affects the capacitance. And if capacitance changes, that should affect, well, something else. In this situation, the question is, what do you think should be happening to electrons? How should they move if they will? If they don't move, you can choose, well, that's 1, 2, 3, naturally. One, two, three. If you think they don't move, that's your answer. If you think they will move, we have only two options. They might move like this, and this direction we call counterclockwise. Or they might move like this. And this direction we call clockwise. And nothing else can happen, right? Unless it explodes. So in this situation, as in any situation in physics, picture is very helpful. So the initial situation had electrons removed from the top plate and moved onto the bottom plate. Now, before we make any change, we also have two options. We can keep capacitor connected to the battery, or we can disconnect it. So the question is about situation when battery remains connected. But what do? We make a change, and in physics, every time when we make a change, it's useful to draw a picture which shows also after the change had happened. And what do? We increasing the area. So distance remains the same, but the area is getting larger, more area. When we make a change, we should make a statement about at the minimum 3 variables, at the maximum more, 5 or 6. So what is involved? Charge, capacitance, potential difference. Where else could have been involved? Electric field between plates and energy stored in the capacitors, area, distance between between the plates and the electric constant. You see how many different variables are involved in this situation in general. But in this thought experiment or app experiment, the only change is happening area. How does it affect? Well, how would you finish this question? If we change area, what should be affected immediately? Yeah, capacitance. Okay. How? More area, more capacitance. Which means now more charge should be stored, right? So if we had like 6 electrons now we should have more so more electrons should be removed from the top plate and pumped down to the bottom plate. So if electrons are being moved from the top plate to the bottom plate, this direction, how do you call it? Counterclockwise. So this type of reasoning tells us, well, in this particular situation, what is happening to capacitance, to the charge. All right, what do you think is happening to the voltage, which, as we know, is just potential difference? What do you think is happening? Someone from that gentleman who looked away. Yeah. What do you think is happening to the voltage? If you reacted, yes, I talk to you. You can say both, wherever you want to. Increased. Now, the gentleman who reacted, what do you think happened to the voltage? Decreased? Decreased. Well, you're both wrong. Again, there is nothing wrong in saying wrong. The wrong is to stick to saying wrong, even if you know you're wrong. The voltage is fixed by the voltage provided by the source, the battery. We will talk about it probably tomorrow, but inside the battery, chemical reactions do something specific. And technically, we don't care what those chemical reactions do. We know that if the battery is not dead, it keeps fixed potential difference between the positive and negative electrons. That's what the battery is. That's the mission of the battery, to keep fixed potential difference until it's alive. So when we have a capacitor connected to the battery, no matter what is happening to the capacitor, the potential difference between the plates is being defined by the battery. So in this situation, remains constant. By the way, if potential difference remains constant and the distance between the plates remains constant, that tells us electric field, which is delta V over D, remains constant. I have more examples like that in the future. First, I want to ask you this question. So use your memory or memory device. And actually, maybe I'll try to fit. Okay. That's what slow computer does. All right. So this is the question, and here I'm going to try to show what we're talking about. I have two capacitors here, two parallel plate capacitors. One, two, Well, technically what I'm doing, I'm completing a circuit. In series, what does it mean? It means, first, I'm connecting two plates of the capacitor to each other like this. And then, well, I could add more capacitors. And then I need the source of the fixed potential difference. And I connect second capacitor. This circuit now is complete. It's alive. And in series means that electrons, if we had this space between the plates filled up with something conductive, electrons could just run through. Of course, in reality, they cannot jump across unless we apply a very, very, very high voltage. In that case, it actually could make a spark. But until then, when I close the switch, what should start happening? Electrons should start be moving, because this element works like a pump. And if the switch is closed, this symbol represents the battery. A short line represents a minus. You always can read negative electrode. And the long one represents positive electrode, the plus. Again, positive means this electrode provides a high potential relative to this electrode. How much higher? Well, we can read this battery says 6 volts. So potential difference between these two electrodes, 6 volts. It declines in time, of course, but when it's fresh, it's 6. If you have a battery like this, the potential difference between these two electrodes is equal to what? Do you know? 9 volts. All I need to do is just read it. And fresh battery like this always provides fixed potential difference, fixed voltage, 9 volts. I can use a multimeter and measure it. Well, so what did you say? I want to look up your answer to this question. That was the question number 6. 6. Oh, we got all distribution, all possible answers. Well, bless you. All answers are meaningful. This is not the wrong question. But we need, again, to imagine what should start happening to electrons. They cannot jump across. Yeah. So this battery starts moving electron by electron by electron. That's clear. Question is what's happening in between. Well, when this electron, first electron comes here, this plate becomes negative, and it acts, exerts a force of repulsion on electrons on the opposite side, So there's one electron which is being pulled away, and it comes here, and it starts repelling electrons on this side. So there will be one electron which moves over here, and this process is happening again and again. What is happening to it? And again, until each capacitor will be charged. How? Well, if we bring 100 electrons here, and then 100 electrons move over here, and then 100 electrons move over there, what does it tell us about the charge? The charge is supposed to be the same. This is an important feature of capacitors connected in series. When we close the switch, eventually, each capacitor will have exactly the same charge, but of course the voltage across different capacitors will be different. It will be related to the capacitance and the charge. Yes, you had it.
Also, I was going to ask, does it matter if there's different areas or distance between capacitors?
Well, in this picture, just to help us to see what should be happening, capacitors look alike, the same. In reality, it doesn't have to be the case. In reality, different capacitors might have different capacitance, but still, everything will be balanced out in such a way. So eventually, when we close the switch and equilibrium is reached, they all will have the same charge. But now we can use this understanding to calculate different variables related to this situation. Well, first, it doesn't really matter how many different capacitors we use. For each capacitor, the standard symbol is just two lines parallel to each other. That's it. Capacitance could have been different. We connect it to a power supply, to a battery. It doesn't really matter what is the source of that potential difference, or we call it voltage. As we know, each capacitor should have exactly the same charge. That actually is basically an application of a law of conservation of charge. We cannot destroy electrons. We cannot create electrons from nothing. All we can do is just move them from one plate to another. Now, the first capacitor should have certain voltage across the plates. Now, this is the language thing. Potential difference is between. Voltage is across, like across the river, the bridge. It's just a terminology, it's a slang. So when we say voltage, we say the voltage across capacitor. Potential difference is between 2 points. That's it. A part of a language we should commonly use. And of course, for each capacitor, we can write the expression which relates charge, capacitance, voltage. And of course, that's number 2. If we add the voltage number 1 and the voltage number 2, we should get the original voltage provided by the battery. That's another relationship we can write. And now we can use this and do some simple algebra to answer a question. Which single capacitor could we use to replace these two capacitors, but still have the same charge stored, assuming the same voltage is applied. So this is what we want to find out. What capacitance should that new single capacitor have so it would store exactly the same charge if we would apply exactly the same voltage? This new capacitance has a name, the equivalent. Not net, not total. Again, that's terminology, equivalent, which means replaceable. We can replace these two with this one. And the question is, how do we calculate that new equivalent capacitance? Well, algebra. On one hand, this charge should be equal to the equivalent capacitance times voltage, because this equation always relates three variables: charge, capacitance, voltage, charge, capacitance, voltage. But if we replace voltage 1, voltage 2, and voltage with what it's equal to, and it equals to charge over C1, charge over C2, and that should be equal to same charge over C equivalent. And if we cancel the charge because it's the same, the result is this equation. This equation tells us how to calculate the equivalent capacitance when we have several capacitors connected one after another in series, like in this situation. Any questions? We're going to do examples, of course. No questions. This is what we call capacitors connected in parallel. So let's take a look. What's the difference? You see, here we have positive, negative, positive, negative. So a negative plate of this capacitor is connected to the positive plate of this capacitor, and there is nothing in between. That's what we call capacitors connected in series. In parallel, it means we connect positive to a positive and negative to a negative. Kind of literally parallel to each other. So I want to connect a positive to a positive and a negative to a negative, like this. And if I want to charge, this room not very good for demonstrations. I just need to connect the power supply to which one? Doesn't matter. They connected already. So get this one, connect it to this. What do you expect should happen to the equivalent capacitance? So see, we could add more capacitors like that. We still would call them connected in parallel. Well, in this situation, the answer actually is very intuitive. Basically, what I'm doing is this. I'm increasing the area, like in our applet. So my capacitance should go up. And let's see if you can see. Come on. I'm going to ask someone to help me to hold this device. Because if I had a third hand, I wouldn't need any help, but anybody could. Thank you. Because all I want to do is just, just make sure it's in the screen. Otherwise, okay. So you can read it. So let's see what we get. Okay. About 20 picofarad. And now, if I touch the plates, it's about 40. Doubled. Very simple. This, of course, simple experiment, thank you very much, tells us that in this situation, we just need to add capacitances of individual capacitors. Well, let's do it very quickly. All right. So what do we have? The same now. Again, two different capacitors. Maybe three, maybe four, doesn't really matter. Connected to a source. Fixed voltage. Now, each capacitor, of course, has a certain voltage across it, potential difference between the electrodes. However, you can see now the voltage number one should be the same as number two, should be the same as just the source voltage. Now the charge should be different in general. How much charge does this system store? This system stores a charge which equals the sum. That's how much charge they together store. And for each charge, we can write the same equation. And of course, now we ask the same question. What single capacitor can we use to replace those two or more, to connect it to the same source and still have the same charge stored? The capacitance of that single capacitor, of course, has the same name, the equivalent. And of course, the relationship between the charge, capacitance, and the voltage should be the same. And now, if we do some algebra again, and I hope by now you start liking algebra, the equation says did you see what I did? These equations had a symbol related to specific voltage, but because it's the same, I don't write any subscripts anymore. And because it is the same variable, we can cancel it out. And the result is this equation. I think it's very, very neat. Yeah. Very physical. It's based on our understanding how a capacitor works. It stores charge, and when it stores charge, the charge is supposed to be related to the potential difference between the plates. The relationship is always the same. The only thing we need to keep in mind, what should remain the same when we make a change. And what capacitors should experience the same when we connect them together. We have two types of connections, in series, in parallel. When capacitors connected in series, we always can replace them with a single capacitor, which has equivalent capacitance like this, in parallel like that. And let's just do example. 3 capacitors. Well, we have to draw a picture. And to draw a picture, we need to know what that word in red, series, means. It means one after another, a negative electrode of a first capacitor should be connected to a positive electrode of the second, etc., etc. That's what is happening. And what we need to calculate is what should be the capacitance of a single capacitor which we could use to replace these 3. We only have 2 equations to choose from. Well, in this situation, we should have 3 terms, or and now you should tell me which equation do we want to use, the top or the bottom. You choose correct equation, the rest is mathematics, relatively simple mathematics. You choose the wrong equation, your work is wrong, which is not a big deal, we can always correct it. Right, but what equation should we use, do you think? What do you think? The first one? We make a choice and we use it. So please use it. 1 over C equivalent should be equal to 1 over 1 plus 1 over 2 plus 1 over 3. I use microfarads. In that case, my answer automatically will be in microfarads. What is a common mistake people might make in solving this problem? One over 1 is 1, 1 over 2 is 0.5, 1.5, 1 over 3 is 0.3, so it's about 1.8, right? If you stop now, that is a mistake. Because you have to make one more step, you have to flip it. Technically, this is how we could write it down. C equivalent over 1 is equal to 1 over 1 plus 1 over 2 plus 1 over 3, 1 over 1/8, 0.8. Someone should tell me the number. 10/19, 5/9. Point 8, 5, 6.
No, it's just 5/6.
Just 0.56. Cannot hear you. Yes, of course. Yeah, you good question. This is the same as, what is it? So the common denominator is 6, right? So, and here we have 3, 2, 1. No, what did I do? I'm crazy. 6, 3, 2. So that gives us 11 over 6. So microfarads, or 6 over 11 microfarads. whichever you prefer. Any questions? So it's all about reading right word and choosing right equation, which corresponds to that word in parallel. All right. That's supposed to be really, really quick calculation, yes? C1, C2, C3 should replace with one capacitor, which should have equivalent capacitance of C1 plus C2 plus C3, 6 microfarad. I believe I have a question now. And why do I ask you questions? So I could get some coffee. While waiting for you to answer, I just want to show an example. Don't choose the last answer. Capacitors do exist. Actually, they come in many different forms. I'm going to show you in a minute. Big, not so big, small, even smaller. Nowadays, every electronic device, your phone, your computer, has hundreds of capacitors, tiny capacitors inside. That's why we need to know how they work. And here, this is a device which can measure capacitance. About one, come on, autofocus, about 1 microfarad. Same here. I could change it a half, 1. This device has a name, a decayed capacitor. And what can I do? I can connect them together. What's going to happen if I'm connecting these two capacitors like this? What do you think will be the reading equal to? What kind of a connection or wiring do I make? Parallel or series? Parallel or series? Parallel. So now it's 1 plus 1, 2. It was 1 plus another 1, 2 microfarads. What's going to happen if I connect them in series? Well, I have to change connection. This is how I want to place, because it's easier for me to connect positive to negative, positive to negative, positive to negative. And now I connect the device across the whole circuit. And now it's a half. It was 1. 1 for each, but now it's a half. So the connection in parallel increases the capacitance of a system. Why? Because of same reason, in parallel, we're basically increasing area. But in series, basically we're moving apart. We're increasing the distance between those plates. Effectively, that decreases the capacitance. Well, in this situation, let's see the distribution. That was the question number what? 7. Survey says well, I tricked you, I succeeded. This is what you should have used. Pictures from your notes. That's how in series looks like. That's how in parallel looks like. This looks neither, because this is how connection in series would look like. But if we are adding an extra element that allows electrons to run, it could have been anything else, just a wire or a resistor. But this doesn't look like this. Do you see the difference? If you see the difference, that means this is a different connection. So the answer is neither. It's not in series, it's not in parallel. So when we have a combination of elements, in this situation, we have a combination of capacitors. We have to be very careful. And we have to look for at least two elements which are definitely either in series or in parallel. Do you see some clear connection? How connected? In parallel, exactly. So this is what we should look at first. These two definitely connected in parallel, definitely. Which means we can make a transition. We can replace these two with one, but that one must have the capacitance equivalent to these two. So every transition should lead to a new schematic. Don't have to draw a battery every time, but still. This, and people sometimes write like 1, 3, or 1, 3 equivalent. This one capacitor should replace those two. This is still old, same old C2. But now and only now, we can make a transition one more time, because now these two capacitors connected clearly in series. So this is a standard symbol for an electrode, terminal electrode, a terminal. And this people call equivalent, total, or just equivalent, or 1, 2, 3. You can name it whichever you like. And now we know what to do. Because for every transition, we have an equation we can use. For example, C1, 3 equivalent should be equal to what? Parallel means more area means increasing means adding, C1 plus C3, which is, in this particular case, 4 microfarads. So now this is 4 microfarads, and this is 2 microfarads. To make the transition to the last schematic, what we have to do is this 1 over C equivalent should be equal to 1 over 4 plus 1 over 2, or 1 plus 2 over 4. But we don't stop here. We have to remember, for capacitors connected in series, we have to flip it. And that gives microfarads, or about 1.3 10 to the negative 6 farads, or if you like decimals. But that's not all we can calculate. When potential difference across the system is given, 6 volts, we can calculate the charges, we can calculate individual voltages. Of course, right now we just have to start applying that fundamental relationship, a definition of capacitance Q equals C delta U, as many times as we want to. So, four microfarads, 2 microfarads, 6 volts, and 4/3 microfarads, 6 volts. Here, I can immediately calculate the charge. Q will be equal to C delta V, 4/3 microfarads times 6 volts, 8 times 10 to the negative 6 coulombs. Where that charge would have been collected. It would have been collected on these plates if we had all 3 original capacitors replaced by this one. We could have done it. But now, we know that exactly same charge, if we make a transition back, should be stored here, which automatically also means here. And here, this charge has a name. Here, this charge has a name, Q2. So this voltage has a name, delta V2. And we can write the relationship between the charge, capacitance, voltage. But now we can use it for calculating that voltage. Times 10 to the negative 6 over 2 times 10 to the negative 6, 4 volts. Again, V, voltage, volts, Voroshilov. Don't confuse those V's. They're different. And now we're in the situation when we have more equations we could use. For example, I can immediately calculate the voltage across the first capacitor. How? Because first and second together should give the total. So if the first and second should give the total, the first should be equal to total minus second. But now we can go one step back. This is supposed to be 2 volts, and this voltage is 4 volts. And now we can calculate each charge individually, charge number 1, charge number 3, because we know the capacitance and we know the voltage, and charge equals capacitance times voltage. But if we add this and this, we should get the original. The law of conservation of charge says us that total charge stored, let's say here, should be equal to the charge here. That's what the word equivalent means. If we're replacing 2 with 1 and everything's supposed to be equivalent, the same. So Q1 equals C1 times delta V1. Q3 equals C3 times delta V3, which is the same as V1. And that's I'm not going to calculate. It's very quick, and I'm not going to ask this question because we are almost done. First of all, the note at the bottom says this is a different problem, a new problem. And the question now is about these two capacitors. And the answer now again is the same. Capacitor number 1 and capacitor number 3 are not related. In this situation, capacitor number 1 is related to capacitor number 2. So in this situation, C1 and C2 are in series, and C3 is parallel to those. So first transition. Well, this is 3 microfarads. And capacitors 1 and 2, now I can replace. Well, that should be 1 over 1 plus 1 over 2. 2/3 microfarads. And now I can make one more transition. These are in parallel, so now I'm just adding the capacitance. And the new equivalent, the total equivalent capacitance will be 3 plus 2/3 microfarads. And across this equivalent capacitance, if we apply the same voltage, we should get a certain charge. But this charge actually should split between these Q1, Q2, Q3, and Q2 and Q3 that together should be equal to that Q, a law of conservation of charge. But if we look at this picture, Q1 should be equal to Q2 and delta V1 and delta V2 together should be equal to delta V3, which is the same as total. You see how many expressions we can write? And the rest is just plugging numbers in and calculating, step by step, step by step, step by step. I believe you have a very similar homework problem, so you can practice using this approach. What should I write? You know what should I write? I should write right now, physics is done. So from that point forward, it's your problem, not mine. All right. This picture is very similar to a picture you have seen before. But now, instead of adding a charge to a conductor, we are placing a conductor in a strong electric field. And we've done that before. First, I need a strong electric field. Yeah, this room is not very... All right, we can see both of them. Good. First, I need a strong electric field, and we know how to do it. Just rub. All right. And we know why that's happening. I do not change the charge of the electroscope. It still remains neutral. But I push electrons down, and we can see that electric field changes electron distribution. Now, if I use a shield, just cage, yeah. Let me out, let me out. I will. Just do your work. So this, you see, still getting affected. Nothing. Nothing at all. Electric field cannot get through the cage. Sound, air can, but electric field can't, and this is the reason. We know that, well, before we said that the surface of a conductor should have the same potential, otherwise electrons would move. But now we can say that even inside of a conductor, the potential has to be the same, constant, because otherwise it would exert, well, it would generate electric field, which would exert force on electrons, and electrons would move, and that's not an equilibrium. So in equilibrium, potential should be constant. Delta V, potential difference, is 0. Delta V over D, 0. No electric field. And yeah, in the basement, plus this is already kind of cage. It's really hard to... Well, you can hear it. And now nothing. This is a standard demonstration which people use to prove this fact. And why? What's happening? Well, electromagnetic waves, radio waves, we're going to talk about. It's just a form of electric and magnetic field together, and it just cannot penetrate even through the cage. The first person who realized that was Faraday, Michael Faraday. So a cage like that actually has a name, Faraday's cage, but he didn't use it for anything but experiments. And Faraday's cage is basically your car if you're inside it. And if a thunderstorm is happening, if you are inside your car, you're safe, because the electric field cannot get through. That includes lightning bolt. Well, any questions? In that case, let's finish today. I'm going to pick up tomorrow from this. Thank you very much. You're free to go. Yes.
I remember in my country, when in the countryside they used to have the big TVs, and whenever they wanted to catch the radio, like they wanted to like see the channels more clearer, they used to like stick a metal. Right? And he was like, oh, guys, if you take let's die today.
Yeah, I was like, she was like, okay, are you having a future? I'm like, I don't know where I'm going. This is going to be a
It specifically said, like, you turn, like, no.
Potentially the same thing. With a fused